Welcome to this video. We're going to learn about sensors and what role they serve in circuits. A sensor, just as an overview, is a device whose resistance changes based on an external stimulus. External stimulus. That can be like a change in the temperature. It can be a change in how much light there is in the room. It can be a lot of different things. And in fact, there are many different sensors which respond to different stimuli. In this video, we're going to look at two. Our first is a negative temperature coefficient thermistor. That's a fancy word. We will often just call it a thermistor. There are positive temperature coefficient thermistors, but we don't study those here. So a negative temperature coefficient thermistor is a device whose resistance decreases as the temperature increases. Okay. Let's make a graph showing that fact. We are going to change the temperature and measure as our dependent variable the resulting resistance in the thermistor. Now I've written a little key at the very bottom. The resistance is low when it's hot. The resistance is high when it's cold. Okay? So let's start out at the left side of the graph. Let's say it's really, really cold. So I'm going to use a blue dot. Here the temperature is 0. Maybe it's 0 degrees Fahrenheit or something. And the resistance is high, right? And as we increase the temperature, the resistance goes down. As we increase the temperature some more, right, the Y value, the resistance goes down some more. And eventually, we start to get pretty hot. And the hotter we get, the lower the resistance. And then we're really, really hot, and it's really low, the resistance. So on the left side of the graph, it's cold, because the temperature is so low. On the right side of the graph, it's hot. And you don't need to draw all these dots if you don't want. The general shape is this. Okay? This graph is not needed for IB. The reason I've included it is because I think it's a really nice way of visualizing how a thermistor acts as we change the temperature. But this is one of the very few cases where you'll ever hear me say you can ignore this for IB. You don't need to study it for the test. All you need to remember is these basic points right there. This symbol, we draw thermistors in a special way when we are making a circuit diagram. Okay? A thermistor is it's like this. We have our regular resistor. And then we have a line that goes down and across like that. Or sometimes, let's see, sometimes it might be more, this is a better drawing. That's better. That's how our thermistor is drawn. The next one, the second and only other one that we'll see, is a light-dependent resistor. That's a device whose resistance decreases as the light intensity increases. So we can make a nearly identical graph. Here's the temperature. I'm sorry, not temperature anymore. On the x-axis is light intensity. And on the y-axis is resistance. The resistance is low when it's bright, and the resistance is high when it's dark. Okay? So the light intensity tells us how much light is shining on the LDR. If there's not a lot of light in the room, that means we're on the left side of the graph and the resistance is high. As we make more light, as we increase the light in the room, the resistance, the Y value, goes down. If we increase the light intensity, make the room even brighter, the resistance goes down even more. And the graph looks almost the exact same as the other graph we previously drew. Okay. The symbol that we use for an LDR is like this. We have just a regular resistor and then two lines coming at it like that. Those lines represent the light hitting the resistor. Sometimes you'll see a more complicated drawing where there's like a circle and then a resistor inside. And coming at the circle are the two lines, the two arrows. So both of those are valid drawings. The one that we'll usually use mostly is the one on the top. Okay. Now I want to show you a couple of really simple problems involving these. Okay, so the last thing I want to do here is answer a couple of questions. Let's say we have a really simple circuit like this. An EMF source connected to a thermistor, and it's a negative temperature coefficient thermistor. We're asked, as we increase the temperature, what happens to the total current? Well, with thermistors, as the temperature goes up, the resistance goes down. If we decrease the total resistance in this circuit, then there's going to be a lot easier, it's going to be much easier for current to flow, and so I total increases because charges have an easier time flowing through that circuit where there's less resistance. What about this one? We have another really simple circuit, an EMF source connected to an LDR, a light-dependent resistor. We're asked, as the room gets darker, what happens to the current in the circuit? The light intensity is going down, right? There's less intense light. It's not as bright. And therefore, we know the resistance of that LDR does the opposite. It goes up. If we increase the resistance of this circuit, then charges have a much harder time moving through and flowing. Therefore, the total current, I total, will be less. It decreases. The total current decreases. Now you're going to do some other problems where you're going to have to think through things in this way. I encourage you to write out these kinds of notes when you solve the problems.